Hello everyone, my name is A. Jabali Reddy from CSC AIML A section. Today, my tech talk topic name is minimum modulus of an N-naught matrix. Minimum modulus principle. For a holomorphic function f on a connected open set D of C, C means complex numbers, if Z0 is a point in D such that 0 is less than f of Z0 is less than or equal to f of Z. For all Z in some neighborhood of Z0, then f is constant on D. So to prove this, we need maximum modulus principle to 1 by f. So we need to apply that. Apply the maximum modulus principle to 1 by f. Then we can prove minimum modulus principle. Let f be analytic on a domain, union, a subset, or equal to complex numbers, and assume that f never vanishes. Then if there is a point z0 that belongs to U such that f of z0 is less than or equal to f of z, for all z belongs to U, then f is constant. Let U is the subset or equal to complex numbers be a bounded domain. Let f be a continuous function on the closed set U bar that can also be called as union bar that is analytic on U, and assume that f never vanishes on U bar. Then the minimum value of modulus f on U bar, which always exists, must occur at dou U. In other words, minimum of f modulus at U bar is equal to minimum of f modulus at dou U. Geometric modulus principle for polynomials. We characterize the ascent and descent directions for the modulus of a complex polynomial p of z at an arbitrary point z0 in the complex plane. We prove that when p of z0 is not equal to 0, the cones of ascent and descent direction partition the unit disk centered at z0 into alternating sectors of ascent and descent, each having angle pi by k, where k is greater than or equal to 1, is the smallest index of p bar k z0 is not equal to 0. Applying this geometric modulus principle, we have new proofs for the minimum modulus principle, the fundamental theorem of algebra, and the Gauss-Lucas theorem. Let f be a continuous function on a closed disk D, and suppose f is analytic on the interior of D. If f is non-zero on D, then the minimum of modulus f on D is achieved on the boundary of D. Proof. Since modulus f is continuous on the closed and bounded set D, the minimum of modulus f on D is achieved by some z0 that belongs to D. We must show that z0 lies on the boundary of D. Suppose otherwise that z0 is an interior point of D, since f is analytic on the interior of D. We can expand f in a Taylor series about z0. So we can write the formula like this. F of z is equals to f of z0 sigma k is equals to 1 to infinity ck into z minus z0 power k, where ck is equals to f of power k into of z0 by k factorial. If all the ck is equals to 0, then f is constant on D, and the theorem is trivially true. Otherwise, let L is equals to minimum of k greater than or equal to 1 is ck is not equal to 0, writing CL is equals to BE par J beta, and f of z0 is equals to AE par J alpha. We have f of z is equals to A into E par J alpha plus B into E par J beta into z minus z0 power L plus z minus z0 plus power L plus 1 into sigma k is equals to L plus 1 to infinity, ck z minus z naught power k minus L plus 1, which is also equal the last term, which is sigma k L plus 1 to infinity ck z minus z naught power L minus k minus L plus 1 is also known as pi of z naught. It is equal, both of them are. This expansion is only valid in a neighborhood of z naught, but we may restrict z to a closed disk d naught, centered at z naught, such that d naught is a subset of the interior of d. Then psi is continuous on d naught, that is subset of d, and by lemma 3, there is a z belongs to means it is belongs to d naught, and that is a subset of d, with f of z is less than a is equals to f of z naught. This contradicts the fact that z naught minimizes f on d. So let's come to the n naught matrix. So let's take a matrix 3 by 3 circular n naught matrix. Following Fedler, let P be a matrix. P is equals to 0, 1, 0, 0, 0, 1, 1, 0, 0, 3 into 3 by 3 matrix. And let CP denote the class of all 3 by 3 circular matrices, that is, matrices of this form. A comma Z plus CW comma P plus A comma P square. Where alpha naught comma alpha 1 and alpha 2 are real, it was shown in the theorem that if A is a 3 by 3 circular matrix whose row sum is 1, then A is uniquely determined by the eigenvalue set of A is equals to alpha naught plus alpha 1 omega plus alpha 2 omega square, where omega is equals to minus 1 by 2 plus I into root 3 by 2. Note that the corresponding eigenvector is 1 omega and omega square power whole to the power t. And the other two eigenvalues are the row sum 1 and z of A bar. Further, it was shown that A is an M matrix if and only if z of A is equals to x plus iy, satisfies x is greater than or equal to I plus modulus of y into root 3. Note that if the N0 matrix A of the form 3.1 is in CP, then N of A is equals to alpha naught plus alpha 1 plus alpha 2 less than 0. Since this is the eigenvalue corresponding to the eigenvector 1, 1, 1 to the power t, that is, if A is equals to ti minus p, where b is greater than or equal to 0, and p of n minus 1 of b is less than or equal to t, is less than or equal to rho of b. Then 1, 1, 1 power t is the parent vector of b. Denote by Cp to the power minus 1. The subclass of Cp consisting of those matrices such that alpha naught plus alpha 1 plus alpha 2 is equal to minus 1. So by this we can conclude that alpha naught plus alpha 1 plus alpha 2 is equals to minus 1. So to prove this, there is the theorem. Theorem is equal to 3.1. A matrix A that belongs to Cp power minus 1 is uniquely determined by the complex number set of A. In particular, A belongs to Cp power minus 1 is a not matrix if and only if set of A x plus iy satisfies. If x is greater than or equal to minus 1 plus modulus of y into root 3, and the second condition is x is greater than or equal to 1 by 2, and the third condition is x minus 1 whole square plus y square is greater than or equal to 1. Proof. A matrix of the 3.1 is in Cp to the power minus 1 if and only if z of A is equals to alpha naught plus alpha 1 omega plus alpha 2 omega square, where alpha naught plus alpha 1 plus alpha 2 is equals to minus 1, which we already proved. The proof of 1 is similar to the proof of given in fourth theorem for n matrices, but is included here for a completeness. If z of A is equals to x plus iy, then x is equals to minus 1 minus 3 by 2 alpha 1 plus alpha 2, and y is equals to root 3 by 2 into alpha 1 minus alpha 2, which yield together as alpha 1 is equals to minus x plus 1 by 3 plus y by root 3. Alpha 2 is equals to x plus 1 by 3 minus y by root 3. So we get two equations from this. A 3 by 3 circulant n-naught matrix A is characterized by the inequalities alpha naught greater than or equal to 0. Alpha 1 is less than or equal to 0. Alpha 2 is also less than or equal to 0. Alpha naught square is greater than or equal to alpha 1 alpha 2. And determinant of A is equals to alpha naught whole cube plus alpha 1 cube plus alpha 2 cube minus 3 alpha naught alpha 1 alpha 2, which is less than 0. For A belongs to Cp to the power minus 1, it can be shown that the inequalities alpha 1 is less than or equal to 0 and alpha 2 less than or equal to 0 are equivalent to 1. The inequality alpha naught greater than or equal to 0 is equivalent to 2. The inequality alpha naught square greater than or equal to alpha 1 alpha 2 is equivalent to 3. And the inequality determinant of A is less than 0 always holds. So by this we can prove that three conditions are satisfied and the theorem is proved. The region defined in theorem 3.1 is depicted as in the shaded portion. So this diagram, the figure here shows that the three conditions are satisfied and the shaded part is the theorem values we got. Thank you.